Thank you, and sorry for the long title. So thanks to the organizers for putting together this wonderful program and for this nice workshop where I can present this upcoming work in collaboration with Miriam Svetic that we were working on basically during the cooler times of this year. So it's just 13 slides, so I hope you will survive. I have my AC here, and I will see you dropping dead. Okay, so this has, of course, so the idea of this project was a little bit to make some incremental progress in understanding 4D n equal to 1 in the context, which I think is an important thing, not just for the swampland, but of course for the landscape. And I think that's where we still need to understand quite a bit. Because to describe theories of gravity, oftentimes we rely actually on extended supersymmetry, because that allows us to actually make concrete statements. We can, for example, use geometry and all these things because we can trust them to the full extent. For example, in describing the BPS spectrum, classify phases of the moduli space. And if we have enough supersymmetry, we basically know, for example, in the case of 4D n equal to 2, that our moduli factorizes, so we can actually describe at least part of our theory or certain sectors of the theory exactly at the classical level. And I guess this is also in the context of both landscape and swampland. It's a very interesting and well-studied case. For example, the vector multiplet moduli space, Calabi-Yau. Calabi-Yau compactification of type 2 string theory is very well understood. Were also the first arenas where maybe in the resurgence of the swampland when it comes to distance conjecture or emergent string conjecture, where the first tests were actually very exhaustively performed. But of course, the more interesting case for both the landscape and the swampland should be, say, 4D n equal to 1, or ideally n equal to 0 if we want to go there. But this comes, of course, as a price, because we know that we do not have such a nice factorization, and we actually need to describe the full moduli space, or I would call it a quasi-moduli space if we accept the presence of potentials. We have quantum gravitational effects that basically mix everything with each other, such that a classical description of any sector is not necessarily there. And of course, there's the question that is very important to answer in this context. What is the difference between n equal to 1 theories and n equal to 2 theories? How much can we carry over from what we know about the n equal to 2 theories to the n equal to 1? So was there a question? No. As I said, so a popular arena of study are Calabi-Yau compactifications of string theory. For example, if we take type 2A on a Calabi-Yau 3, we get n equal to 2 in 4D. We know that our moduli space at the two derivative level splits into a vector and a hyper. One can be, since the dilaton is only contained in one of them, the other one can be described exactly at the classical or geometric level. And we can, for example, we can basically describe this vector multiplet moduli space without having to specify the four-dimensional string coupling. And we can say, okay, everything that we compute in the Kähler moduli sector is independent basically of the four-dimensional string coupling, so we can tune it as we wish and still rely on our results. In particular, we can trust perturbative string calculations also in the interior of the Kähler moduli space. Now, if you were to compactify instead of the type 2A string, the heterotic E8 times E8 string, which is very similar in many regards to the type 2A string, the classical moduli space is still given by the dilatant geometric moduli of X3 and, for example, gauge bundle moduli. And so even if we take the simplest choice for the bundle, where we just identify the bundle with a spin connection on our Calabi-Yau threefold, we have what is called standard embedding, and we break our gauge group E6 to E8, and basically the classical moduli space is very similar to the type 2A case because we do not have to worry much about the bundle moduli. So this is already almost an n equal to 2 example because the worldsheet theory has enhanced supersymmetry in this case, but we can already see in this very simple example clear differences between the heterotic and the type 2A case. How is that? So we can even take an even simpler example and consider a very simple Calabi-Yau, which is just T6 modeled by some group, so for example Z3, some orbifold group, and we can focus on a simplified moduli space that is the complexified over Kähler modulus of T6 and the 4D heterotic dilaton. So classically, one would now say, okay, we can take S in type 2A, we could just vary the Kähler modulus independently by keeping the heterotic string coupling fixed, which is just like one of these infinite distance limits that we would have in type 2A. But however, here comes the difference between the heterotic and the type 2A situation, because on the one loop level, these guys, even though they're classically decoupled, they mix through threshold corrections to the gauge couplings of the heterotic gauge groups, which are, of course, known since the very beginnings or since the 90s. Which are basically tell us that the gauge coupling in the various gauge groups is the three-level result, which just identifies it with a heterotic string coupling, plus one loop threshold correction that here depend on the geometric moduli, hence mixing the two. And for this very simple example, of course, these corrections have been readily computed just briefly after, and they take this nice modular form. So what does this mean if we now go to the large T limit? We can expand basically the Dedekind eta function I had on the previous slide, and we get something like this. So this perturbative analysis suggests that now we encounter a strong coupling singularity for the unbroken E8 vector, basically at some maximal value for the Kähler modulus, which is something we do not see, and we don't have an analog for that if we have high extended supersymmetry. So in particular, one cannot reach the large volume limit at finite heterotic string coupling, unlike in type IIA, where we just would get an M-theory decompactification to 5D M-theory. Yes? It's one loop plus non-perturbative. I will come to, but I mean they computed the one loop threshold correction. So this is why this is just a perturbative analysis, and I want to see how what happens to this at the non-perturbative level. So this perturbative analysis suggests that there's a strong coupling singularity for the hidden E8 gauge factor at real codimension 1. So one would, yeah. Yeah. So here I just put it to make it obvious that this is this guy for this very simple model where actually we know the beta function, which is negative, and I just put it here to make it obvious that this is a negative. Of course, in principle, it depends on the exact theory that we look at, but for the simplest case, exactly. Just for the simplest case, I just wanted to make it clear that this is that you don't have to go at this heat through the exercise to think okay, what is my beta function, and is this positive or negative? But there could be other cases. In the simplest case. No. It's not necessary, but in the simplest cases, it is exactly like that. So in the simple cases, one would then ask, okay, does actually the modular space end at this real codimension 1 singularity, strong coupling singularity in the modular space? And similar, if you look at these, also around the same time, at these papers where of Dieter, Anna Maria and friends, where they compute the non-perturbative superpotential, you would also say, okay, actually along this guy, the superpotential is of order of my string scale, so I should not actually really trust my effective theory in this regime. Okay, so the perturbative analysis suggests that there's a real codimension 1 singularity, but of course my modular space itself is complex, and when we would expect on general grounds that it just has complex codimension 1 or higher singularities, which is of course in contrast to this real codimension 1 singularity. But to see actually how this is solved, one would need to involve non-perturbative effects that go beyond the perturbative analysis I was just mentioning. And actually, we already know that something similar happens in n=2 theories. There, if you compactify type IIA on a Calabi-Yau, also know that classically the Kähler modular space of a Calabi-Yau threefold ends at loci where divisor shrinks to 0 size. Basically, you know this is what happens in the analog M-theory. If I, instead of type IIA, look at M-theory on a Calabi-Yau 3, I take a limit where the divisor shrinks to 0 size. My modular space does not get any corrections. I know my classical modular space ends there. But at the quantum level in type IIA, taking into account worldsheet instantons, the modular space actually does not end, but we can go around or the real codimension 1 singularity gets resolved into a complex codimension 1 singularity, and we encounter new phases, for example, orbifold phases. So,
why do you only expect to have
I would expect that in a complex modular space, I should always be possible to go around a singularity, because I would like that all the expressions are analytic in some way. Yes. I expect the potential. I do not need to assume. I would call this a quasi-modular space. So basically, I have a scalar. Maybe I call it a scalar field space or quasi. I do not need to assume that the potential, but also the potential analysis would suggest that I actually should end because my potential would diverge, and then. But you could still ask, okay, if I had enough energy, I could go there, and I could ask, could I actually, does my potential, what does it actually diverge, or does it actually decay again? So I would say, okay, let me first ignore the potential and say, okay, what would be the classical structure of my field space? Yeah. That which expression will be positive? This guy. But you could still ask, is there? I mean, is there a regime? Does it actually, or what happens around this corner? Of course, you would say if I have a runaway, but this is of course also the interest. If you say, okay, do I actually need to go always to runaway, or can I have a more non-trivial potential in the interior? Also, actually, how does the potential behave around this singularity is another question. So via duality to F theory, the strong coupling singularity actually can be mapped to a point where if I have F theory on an elliptically fibered Calabi-Yau fourfold, a divisor and the base of this elliptically fibered Calabi-Yau fourfold vanishes, such that actually it looks very similar to this situation in the Type IIA case. But of course, the problem is how to compute actually the quantum effects in either the heterotic or the F theory duality frame. And so the approach that we took is to use yet another duality, and instead of the heterotic F theory duality, use duality to the heterotic M-theory case. So we all know that heterotic on X3 is dual to M-theory on X3 times S1 mod Z2, with the gauge theory realized on the end of the world branes of this interval. So for standard embedding, which is what I'm mostly interested in because it's the simplest case, I have a non-trivial and opposite M5 brane charges at this end of the world branes, which shows us a non-trivial profile for the Kähler model of X3 over S1 mod Z2. And so in the following, I will just focus on the overall volume of V of the Calabi-Yau, which in the 5D n equal to 1 parent theory, so if I just compactify M theory on X3, results in the universal hypermultiplet. So I have I can define this complex field V, which is the S, which is the volume, plus the axion dual to the 3-form in 5D, and some 3-form and some periods of the Type IIB M theory 3-form. Now, heterotic M-theory duality actually tells me at classical level I get a duality dictionary that identifies basically the background value for V, which is the real part of S, with the heterotic dilaton, and the length of the interval with a rescaled version of the single Kähler modulus of the Calabi-Yau threefold. Okay, it's nice, but I should not destroy it. Yes. So you can look at the effective action of the 5D theory. So we have here the hypermultiplet sector, which of course depends on the actual metric on the universal hypermultiplet. And at the classical level, this can be described through a classical Kähler potential, which is just the usual minus log S plus S bar. And I have some induced brane charges, which at the end of the day just depends on the second Chern class of the Calabi-Yau threefold, and I have some localized or on the bound state. So this is basically the tension of the end of the world branes and the Young-Mills theory on this theory. And now at the classical level, I know I can make an ansatz for this domain word solution, just the 5D warped like a 4D times the circle, and give some profile to the volume modulus, and I solve the BPS equations using the scalar potential. I, at the end of the day, get a very express everything in terms of these harmonic functions, which depends, of course, on the sources that I put in here. And I find the solution for the warp factor and the volume dependence, the y dependence of the volume. So, of course, this domain wall solution has a profile, and the gauge coupling of the unbroken E8 gauge group is just the value of the potential at the end of the interval. And so I get a strongly coupled E8 gauge factor. Actually, by looking at this alpha parameter is negative, because the second Chern class is positive if I integrate it over Calabi-Yau, and this enters here. And so I get a maximal value for the length of the interval given in terms of this parameter, which is positive, and so which at the end of the day reproduces, tells me that at rho max also the warp factor vanishes for my solution at the location of the E8 domain wall. So I get some, like I get an end of the world brane, and I cannot go beyond that point, at least classically, which reproduces my classical real codimension 1 boundary of the 4D classical modular space. So now, using the dictionary that I had on the previous slide here, one can show that the appearance of this end of the main domain wall actually maps exactly to the strong coupling singularity in the heterotic modular space. You can do the exact map between the scalar fields. And now the point is, in this setup, we can actually look at the quantum effects beyond the classical level, at the non-perturbative effects, and see how they resolve this codimension 1, real codimension 1 singularity at the level of the domain wall solution. So how does this work? We now need to take into account instanton corrections that correct the domain wall solution to their effect on the universal hypermultiplet. So I'm not directly computing instanton corrections to the effective n equal 1 4D action. I'm actually computing and using the results, existing results actually in these papers, on the corrections to the n equal to 2 hypermultiplet or 8 supercharges hypermultiplet sector that enter this domain wall solution, because I basically choose a slice for this domain wall solution in my hypermultiplet sector. So the classical domain wall solution assumes a Kähler potential for the field S that is given by this form. And this is at the end of the day what drives this end of the world domain wall behavior, that both the gauge coupling on the brane and the warp factor vanish. The hypermultiplet modular space is of course quaternionic Kähler and hence does not have a Kähler potential. So what do I do if I actually want to do this properly? But at least, so how do I describe the instant corrections to the domain wall solution? The key is here that we focus on a certain slice of the universal hypermultiplet, for which the metric can actually be written in this simple form. This was discussed in these papers, which is named after this guy, Przhanovsky. And actually, here we have two complex coordinates, and h alpha beta bar is derived from a single function that basically acts as a Kähler potential if we restrict to the sublocus Z2 equal to 0, which can be described as a Kähler submanifold of the universal hypermultiplet. So on this locus, which is the one that we're interested in, we identify the other coordinate Z1 with this S parameter or this S field that I had previously that should vary. And the function H, or the Kähler potential for this vector S on this slice is given by this simple form, which basically is just the 5D dilaton in the 5D parent theory, n equal to 1 theory. So classically, this R, or this 4D dilaton, is just or the 5D dilaton in the 5D parent theory is just the real part of S, but M5 and M2 brane instantons correct the relation. These instantons can actually be computed explicitly, since they effectively correct the universal hypermultiplet modular space. So I do not have to actually do a 4D n equal to 1 analysis to get them. The detailed analysis I think the state of the art is in this paper, and I spare you and myself to go through the details in this afternoon. But the upshot is to take into account the instanton correction, the relation between R and S gets corrected. So we have here, this is the classical relation, and then we get M2 brane instantons and M5 brane instantons. This one are the one that I'm most interested in. So we should now view the Kähler potential as an implicit function of S, which we get by inverting this relation between real S, or like S actually, and R, which is a function of R itself. And then if we would invert this, we could actually compute the Kähler potential. But the question we want to answer is here, do the instantons actually resolve the strong coupling singularity that I had before? So we can consider again the domain wall equations of motion, which take the simple form where here's just certain derivatives and the inverse of the scalar potential. This is the warp factor, and this is the field that runs. So the profile for S is still determined by the sources because that's what the source is coupled to. So it still has this form. And the quantum corrections now enter through the scalar potential derivatives on this side. So these are the equations. So this is the scalar potential that implicitly depends on S. And so classically, we see that A of y goes to minus infinity because S goes to 0, because then R and S are just identified. So, however, since S of y is 0 at some finite y, or which I call y max, A of y max, so the warp factor, is finite if the scalar potential and derivatives remain finite as S goes to 0. And I also spare you here the discussion, but studying the leading instantons, we argue that the scalar potential and the derivative are finite as S equal to 0, basically because we show that this guy remains finite as we take S to 0. So that means that also the end of the world brane, or this warp factor, is finite at the as S goes to 0. And we just get a finite curvature cap off at the brane at S equal to 0. Hence, we do not have an obstruction to go beyond that point, and we do not have an actual boundary of the moduli space. Still, the E8 gauge theory should still be strongly coupled because this is still the gauge coupling on the E8 brane. But we cannot continue beyond this because we would need to somehow describe the new phase of the theory where naively the gauge coupling becomes negative. So we need to somehow describe the confined phase. So to conclude, we studied the strong coupling regime in 4D n equal to 1 theory at the level where we basically treated the moduli space or the scalar field space as a moduli space. The classical or perturbative analysis suggests the existence of a strong coupling singularity not present in the analog n equal to 2 4D theories. And at the perturbative level, the moduli space would thus have a real codimension 1 boundary. In a dual M-theory picture, the boundary of this moduli space manifests at the classical level as this end of the world brane, that we just know from the classical thing. And actually, M-theory captures the full perturbative heterotic analysis. The classical M-theory picture captures the full perturbative analysis, including one-loop terms. But the non-perturbative corrections in the dual M-theory to the domain world can be computed because we know the corrections to the hypermultiplied moduli space of the parent 5D n equal to 1 M-theory compactification. And the upshot is that the non-perturbative correction resolves this end of the world brane, allowing to continue past the strong coupling singularities, hence turning a real codimension 1 boundary in a complex codimension. Of course, questions remain. First, what happens to the potential? Does this also somehow get regulated, and I don't actually get a blow up if I pass beyond this strong coupling regime? And what is this new phase? Because, for example, in the case without gravity, this strong coupling regime of 4D n equal to 1 theories in M theory can be described as already known since this paper in terms of geometric transition. And an obvious question could there be what happens in the case with gravity? Thank you very much.